Hi, this is Paul Schreiber from Synthesis Technology. Welcome to part 2 of our show on reverse engineering the Alesis MidiVerb. Today we're going to talk about the electronic side, and in part 3 we're going to talk about the software side. The electronic side will be divided into 2 sections. The first part will be a general discussion on how we approached trying to figure out the schematic for the MidiVerb with not having anything to go on. The second section, we're going to actually go over the schematic and show you in detail how we figured out how the MidiVerb actually worked. So what do we mean by reverse engineering? Well, this means that you don't have a schematic for a piece of equipment, and you either need to repair it, which is very common with musical equipment. You have some old piece of gear from the 80s. There's no schematic, the company's long gone, or it was a secret. Or in my business during the day, sometimes we have to replace something. Someone comes to me and says, I want you to replace this old pump motor controller. We've been using it for years, but the company isn't a business. We just want the function. In other words, we really don't care how you do it. We just want it to fit into the case and have the same input and output controls. You can do whatever you want to the guts. We just want it to work. In our case, we're doing research. So that's the third R. So you have repair, replace, or research. And in our case, I was always curious, ever since one of these came out, how does a bunch of chips make reverb? I know how a spring can make reverb, but how does a bunch of chips make reverb? And it's always been an industry secret. You're not going to have detailed explanation from Eventide and Lexicon. You're not going to have schematics with source code listings for those products that talk about what's inside their custom chips. This was the only reverb I know of, except for maybe the Quantec QRS Rim Simulator, that didn't really try to hide it. What they tried to do is make it so complicated, people just gave up and said, forget it. Well, even though this is a fairly small and inexpensive reverb, Keith Barr, the designer, did a pretty good job on making it complicated on purpose. We'll find out there was another reason he did that, not just to hide it. So how do you even begin reverse engineering something like this? Well, it turns out that all you really need is a little voltmeter. And you're not going to use it to measure volts or resistance per se. We're going to put it in what's called beeping continuity mode. So what this means, if you just take the leads and you touch them together, you get a beep. Now sometimes you'll hear it go like this. That's because you're bouncing it. Switch bounce, lead bounce. But when you make hard contact, you're getting a steady tone. That just means there's some minimum resistance between the leads, and each meter is different. Usually if it's less than, say, 20 ohms, it'll beep. So how are we going to do that? Well, what we're going to do is first we're going to study the chips that are on here. Now we have an advantage that the chips here are clearly marked. They're not erased, they're not rubbed off with sandpaper, they're not labeled funny, they're not encased in epoxy. They're right there for the world to see, which means we can go on the internet and pull a data sheet for every single part. So that tells us 2 things: what the part's function is and what each individual pin is. Then we can go into, my case, dip trace or schematic capture and pull these parts out of the library. If we don't have one, we can make it from the data sheet, and we can start, and even though this is kind of hard because there's so many parts, we can actually put every chip on a giant sheet of paper and say, here's what we're going to do now. As we hook them up, we're going to move them together and connect them. I did something in between. I divided this into sections, but that's what I did. Was I looked at the parts, I looked at the data sheets, I put them into dip trace, and I started hooking them up. Some cases we don't have that luxury, but we do in the case of the MidiVerb. So where do we start? Well, the first thing is, what's important when we reverse engineer? I didn't particularly care that much about the analog section. I'm not trying to duplicate the analog section. I don't care that much about the power supply. It just has one. Happens to be kind of weird, but it does have one. I was more interested in what the processor does and how does this over here make a DSP. And I figured the easiest place to start was with the microcontroller in the 7-segment displays. How hard could it be? 7-segment displays are an industry standard about what you call the digits, and we have a standard microcontroller, very simple. There's lots of data. You can go on the internet. This happens to be an 8031, it says so right there. You can pull up 8031 schematic, and you'll see they always tend to have three things on the schematic: a microcontroller, the EEPROM for the code, and a latch. And that latch is what latches the address and data into the EEPROM. So we have those things as well. So I really didn't have to study that schematic. I did a quick check to make sure it's what it was on the internet, and there you go. How does it turn on the LEDs? Well, they're multiplexed. You have resistors. You can look at the part number for the LED right there. It's common anode. So that means that the anodes are tied together and you turn each segment on by pulling the cathode down to ground. All right. Usually there's a transistor to do that, but over here there's not enough transistors. So I wonder what they did. So I said, there's an HC part, and HC has a lot of drive to drive LEDs. So I'm guessing those resistors connect up to those segments. So that section I really didn't spend that much time on. Now I had to do it to make the schematic complete, but I wasn't worried. I was worried about the rest of the stuff. So where did I start? I started up here at the top with these two chips. This large chip and the smaller chip both have AMD logos. I looked them up and I found out this is a 12-bit D to A converter, and this is what's called a successive approximation register. There's no A to D converter. Audio comes in, audio goes out. Well, we know audio goes out. Well, there's a DAC. Well, stereo, there's only one DAC. That's interesting. But where's the A to D converter? Well, it turns out what this chip does is it turns a D to A into an A to D by running its little, there's actually a little, what we call a state machine in here, that runs a little series of instructions very fast, and the DAC and this comparator right here form an A to D converter. And so as long as it runs fast enough between our sample period, it'll convert. Well, there's only one DAC, stereo in, stereo out. What's up with that? Well, it turns out that it's not true stereo in. They mix it. So the first analog thing I did was I debugged that real quick and said, there's only one analog input. They're cheating. But it has true stereo outs. We'll talk about that. How does it get true stereo outs? And the answer is, with only one DAC, they do a little software trick. So the section up here, I said, I kind of understand it. I have no idea what's going on down here. So where do I start? So I decided to start at the bottom left corner chip. And it turns out it's a 273, which is an 8-bit latch. That means 8 bits a day to go in. There's a clock signal, and it holds the value, and 8 bits go out. I also started looking about symmetry. You can see there's a wide gap right here on the board. It's like this part is laid out in a block, and this part over here is laid out in a block. And I said, that's very Keith Barr. That's the kind of stuff, if you look at the ADAP, that's the kind of stuff he did. It's very block diagram. Here's some stuff, here's some stuff, The analog stuff is at the top. Power supply is in a block. See how it's all nice in little blocks? I said that's probably a clue. Turns out it's a very big clue. The other thing is, if you notice over here, everything tends to be in these octal parts. Octal means 8 bits. These are octal parts, octal parts, octal parts. This is the memory. The memory is 16K by 4 chips. There's 4 chips. That's a 16-bit data in the memory. That's unusual because it's only a 12-bit converter. Why do you need a 16-bit memory? Why don't you just do that? Save yourself a chip. Over here, nothing is octal. This is all just inverters and flip-flops and NAND gates, what we call combinatorial control logic. Down here, there's some counters that are right next to this EEPROM. I wonder why. Why would you put counters by an EEPROM? There's no counters over here. There's counters over there. This is what we did before we even started looking at how is it hooked up. You see if there's visual clues that the designer gave you on the board, because all engineers who do audio think in terms of flow. Signals flow this way or they flow that way. They come in over here and they go out over there. It's very unusual to have it totally scrambled up like that. It's just the nature of how we think. And so what I decided to do was to start down here with this chip and work my way up and saying, this is going to be our quote, our DSP that's going to control our memory. And the logic over here is going to be our control signals. We're going to figure out what the timing is. When do we stick data into the DAC? When do we turn on the SAR to do a conversion? When do we tell the multiplexer to switch between left and right channels? That's all going to be what we call hard-coded in this logic. And this is going to be basically our computer. So let's start with this part, and we're going to go over the technique we use to start here and wind up figuring out the entire system. All right, for this section, I've kind of zoomed the camera in a little bit, so hopefully you can get a better view. So I want to be like this talking head over here to the side. So what we're going to do is show you the techniques to use what we call beeping. Again, it doesn't matter the quality of your voltmeter. You can use a $9 one from Amazon. It'll still have a continuity beep function. So we're going to start with this 273 down here. Okay? So I'm going to guess that the inputs are going to come from the converter or from the memory or something. What over here is called the D lines. So let's look at the, that's the pinout. Let's come down here and look at the block diagram for a second. So, whoops, one too many. So let's look at the block diagram for the part for a second. You can see it has 8 individual flip-flops, 8 bits of data going in, 8 bits of data going out, a common clear that sets all the flip-flops to 0, and a common clock. This one happens to be rising edge. You can have rising and falling edge. Rising edge will latch everything in there. Notice the flip-flops are labeled 1 through 8. Now, most data bits are labeled 0 through 7, but it's important to know that these are all independent. It doesn't really matter what order you put the stuff in. And then there's a common clock. So if we look at the board down here, if my theory is correct, that means that this flip-flop probably is going to connect to these 2 chips, which if you check, they're 4-bit adders. So there's 8 bits here and 4 and 4, that's 8. So this is a group of 8. And if this is the input to the adder, well, there's another register right here where the output could go. And that's repeated here. It's repeated here. Now, what's unusual, this is not a 273, this is a 574. Is that done on purpose, or is it because he was low on those, or what's the deal with that 574 there? Is there something different between these 8 bits and this 8-bit? We'll have to look and see. So let's see if I'm even remotely correct. All right? So if I'm correct, some outputs of here will go to some inputs over here, and some outputs of the adder are going to come up to here, or maybe to here. We'll find out. So what we're going to do is we're going to look at the first data output, all right, which is called Q, which is on pin 2. So what I'm going to do is, because pin 2 is right there, so I take my probe, and I'm sorry if you can't see this very well. I don't have an overhead camera because I'm poor and broke. So that's pin 2. So we're going to call a sweep, and a sweep, if you can see, is I'm just going to take this probe and rake it, not real hard, I'm going to scratch the board. I'm going to rake it across these chips. Not too fast, but enough where if it's connected, I'll hear a little blip. All right? So it's not connected anywhere up here. All right? It's not connected. To test that, I'm going to put it on ground right here. And all these chips are tied to ground. So if I take this part way over here and rake it, okay, it rakes on that ground, rakes on that ground. See, that's called raking. See that? I got 2 beeps on that chip because I got 2 pins tied to ground on that chip, and so on. So let's look over here at pin 2, and let's see if my theory is right. I'm going to rake it across this adder, and sure enough, it's on pin 2. Is it anywhere else? Anybody else have it? No, I don't expect it to. What's the next output? All right, it's on pin 5. 1, 2, 3, 4, 5. Right there. Do some raking. Not over there. Oh, it's right there on that adder. So I was right. So 4 bits here, go to 4 bits over there, and 4 bits, the other 4 bits, go to those 4 bits, and so on. And that's true for all this little structure right here. So now we have input latches that go into the inputs of adders. The other inputs, it has to add 2 things together. What's the other thing it's adding? I don't know. And then the outputs have to go somewhere. So that's what you do. Now let's try to figure out where this clear and clock. All right. So I'm going to make another guess that these 2 together make a 16-bit pair, which means the clock and clear should be tied together. Let's see if that's true. Does pin 1 go to pin 1? Yes, it does. All right. So they are tied together. Are the clocks tied together? Does pin 11 go to pin 11? Yes, pin 11 does go to pin 11. I was right. This is a 16-bit set of registers with 16-bit adders that generate a 16-bit result plus a carry if it's needed. But there's not 16 bits anywhere except maybe in the memory, which is 16. We certainly don't have 16 bits of audio data. All right. So what else do we need in our microcontroller DSP, little over here, that could be 24 bits wide? Well, the answer is opcodes don't have to be just what's coming out to decode the instruction. You can have multiple pieces of data within an opcode. So what do you mean by an opcode? That's what we call one instruction line of our program. And it turns out that it's very common in DSPs to have very wide opcodes. I've seen some that are 56 bits wide because the whole point is how fast can you execute one instruction. But if one instruction has multiple bits of data in it, then you can execute that one instruction and maybe have 4 or 5 things all happen at once in the hardware. And that's what is true in the MidiVerb. Every time the opcodes are fetched out of here, only 2 bits of the opcode is to tell what the instruction is, because it turns out there's only 4 things this thing can do. This is essentially a 4-function calculator. So all the algorithms that we have are simply stacked and repetition of only 4 basic operations. That's only 2 bits needed. What's the rest of it? So what can it do with multiple bits in the opcode? It can do things like, well, it's this instruction, but also while it's doing this particular function, I want you to switch the A to D converter to a D to A converter. I want to set the sample and hold for the left input because I want settling time, so the next instruction, which is read the left input, it's going to have time to settle while I'm 1 instruction behind. That's called pipelining, okay? So this is a pipelined DSP where you have everything is aligned, but you can essentially tell it to do different things on the board every single instruction, not just the math, but other things as well. The other reason why we have to have more than 8 bits wide for this is that how do you address the memory? Where do you tell the A to D or the D to A converter to fetch data from the memory? And it turns out that was very cleverly encoded. So we're going to talk about that in the next video, about how do you address the memory. Now most people say, well, how do you address memory? You start at address 0 and go up. You go 1, 2, 3. Like if I have 20 samples I'm going to read from the A to D, I would put them in order. The first sample would be an address 0, and the next would be an address 1, and next would be address 2. That's too easy for Keith Barr. It doesn't do that. So we'll find out what it does. Here's a hint. So what we did, and it took a very long time, and I did it along with my partner Eric Brombaugh, is we very meticulously had our dip trace schematic where we had the parts up. Now we didn't put all the parts in at once. We would say, let's put these parts in, and then let's put these parts in. And let's go to a separate page and put the memory in. But what about the stuff over here? Well, let's see if I can do that fairly quickly. Let's see if I can find out where this clock signal goes, all right, on pin 11. So I'm going to turn this around just so it's easy for me to get to pin 11, all right, which is right here. And I'm going to just make a guess that it comes somewhere out of the combinatorial logic. Now that may be a totally wrong guess. It may be coming from the part right next to it. But I'm going to start over here. And I'm going to do a sweep again, if you can see. I'm just going to sweep across these parts fairly quickly, but making sure I have contact. Wait a minute. I got the one next to it. Right there. And it turns out that's a flip-flop. Right there. That's on pin 6 of a flip-flop. Is it anywhere else? Okay. Without knowing what pin 6 is. Could be an input, could be an output. The answer is no. If I sit here and I scrape across all these chips doing what I call a sweep, all right, that's the only place it goes that I know of. Now that may be wrong, but for now, in my schematic, and here I'll show you the schematic, you can see that I've hooked the flip-flop over to that clock input, all right? And that's what we did. It's very time-consuming. It's part by part, and it turns out that you can't get all of it. So what we had to do to verify the schematic is that Eric wrote a Verilog simulator that says if we're right, the Verilog should be able to execute the code And when it didn't match up, we went back and beeped it again and said, oh, we forgot a signal. Or, oh, that was a mistake. We thought it was on that pin, but when we were sweeping, we were off by 1 pin. And eventually, we got the schematic perfectly correct. So there'll be a link in the email that you received a notification on how to get the schematic. Remember, you paid for it, so it's to your best interest not to upload it to the web. Remember, you paid for the schematic. And that's how we did the MidiVerb. So the first thing I did when I started looking down here in this corner is I said, these are the only parts that are not wide, 8 bits wide. What is that part? Okay, well, it's an LS283. So let's look at an LS283. So I'm not going to mess with that computer anymore. Here's just the data sheet for an LS283. You can see it's a 4-bit adder. So, what are we adding? Well, since they're 4 bits, I can say that's 8 bits, that's 8 bits, that's 8 bits. That's 24 bits. And that corresponds to 3 8-bit parts here. And these 3 8-bit parts here, you can see these are latches. So again, 24. We've got a 24-bit adder hooked to 24-bit registers. Well, this is where it helps to know about DSPs. So the basic building block of all DSPs is called a MAC, a multiply accumulate, which means we're going to take the value in a register, we're going to multiply it times a constant, and we're going to add it back to itself. And that's the basic mathematical function to do a lot of DSP things. Now, notice I said multiply accumulate. I didn't say add accumulate, multiply. Well, it turns out that hardware multipliers, especially back in 1986, were hugely expensive. They had them, but they were expensive. But you can also do a shift and add. So you can do multiple operations of adding and shifting, and you can do multiplication. So if you think about binary numbers, if you shift them left or right one position, that's multiplying dividing by 2, right? So what's binary for the number 2? It's 1, 0. If I shift it one place to the left, it's 1, 0, 0. That's a 4. Shift it again, it's 1, 0, 0, 0. That's an 8. I'm multiplying by 2. But here's what's interesting about DSP operations. Generally speaking, the math is called normalized. You want to do values between -1 and +1 for your multiplies. So how in the world do you multiply by, say, negative 0.6375? How do you multiply something by 0.75? Well, we're going to talk about that in the next series. But we're going to show you now that this hardware can do that. So this is overall what I did with some help from Eric Brombaugh towards the end on how he reverse engineered it. We essentially just used a voltmeter beeping, okay? The scope, all right, turns out, didn't even need the scope. The only time I used the scope was to check some clock signals to see if they were really what I thought they were. But other than that, we used meters in our eyes. Yep, sometimes you can just find it on the trace, but usually you can't. What was interesting about this design is that, and I can't stress this enough, because I've only seen this once before, is that on purpose, Barr did not hook up the data bus, what I call normal parallel. Bit 0 coming out of the EEPROM is always D0 on the part, which goes to D0 of the memory, which goes to D0 of the SAR, which goes to D0 of the DAC, because that's the way you're supposed to do it. Keith Barr said, D0 is arbitrary. There's no such thing as D0. D0 is what I called it over here. I could have called it D311. But we call industry standard D0 is the LSB, the significant bit. But Keith Barr said, no, I'm not going to let that convention hinder my board layout. This is a two-sided board. 4-layer boards this big in 1976 will probably cost $300 a piece. He had a tough time to fit it. There's no CAD. This is all done by hand. And so what he did was he just said, this data bit, this one here, that comes out of the EEPROM, which is our code for the processor, is going to be tied to these chips, and as long as I keep track of it till it comes out of the DAC, I'm okay. That's true for everything he did. The code coming out of here, the memory addresses and the memory and the data going into the DRAM, none of that is standard 0 to 7, 0 to 15, 0 to 23. It's like data bit goes here, goes here, goes here, goes here, comes out. I have to fix it in the code. And that's what he did. And as an aside, the way he wrote code for this processor that he invented is he wrote it all in Z80 assembly language, and then he basically translated it into his own, what we call machine language. There's only 4 instructions you can do, and those 4 instructions in the right order with the right coefficients, what we call a coefficient is what you multiply the data with. At the end, the process, reverb comes out. And to me, that's the most fascinating thing about all of DSP, is how can you have audio come in, you stick it into a buffer memory, you multiply it a whole bunch of times really fast by a whole bunch of numbers, and something completely different comes out than what went in. So I hope you got a feel for how to reverse engineer the MidiVerb. All right, it's basically with our little friend the Roadrunner here. That's what we did. So please study the PDF document of the schematic. You can see what I talk about scrambling. And in the next session, we're going to talk about how it took us even longer to figure out what the code did with the memory. And it's a technique, again, I've only seen once in my life. It's called bunny hopping. Yes, bunny hopping. See you next time.